In this video, we're going to explore confidence intervals for a difference of two means. So it's easiest to think about this in terms of two populations being compared on some numerical value. So let's imagine that we're comparing the grades of some athletes and some non-athletes at a given school. So this data is entirely made up for this example. It has no basis in reality. Let's assume that at this school, we have a population of athletes, and we've measured some of them, but not all of them. We've sampled some of them. We've sampled 225 athletes, and we get an average GPA of 3.1. This will come with a standard deviation. Let's assume that the standard deviation is 1.2, which is quite a lot of variability, but that's possible. For non-athletes, let's assume that we've sampled 400 of them. We get an average GPA of 3.0 and a standard deviation of 1.5. So in order to produce confidence intervals for these, we need to think about the standard errors. So what is the standard error in each case? Well, in this case, the standard error is the standard error of a mean. And so we'll use the appropriate formula, sigma over the square root of n. We don't have sigma directly, so we don't know exactly what sigma is, but we do have the next best thing, which is this sample standard deviation, which is 1.2. So we're going to plug in 1.2 here, and then that's the square root of 225, and we'll work out what that is, and that works out to be 0.08. And so the confidence interval that we get is 3.1 plus or minus double 0.08, which works out to be the interval from 2.94 to 3.26. So this confidence interval means that among athletes at this school, we can confidently say that the average GPA is somewhere in this range. Our level of confidence here is 95% because we have doubled the standard error in producing the margin of error. So that gives us a 95% confidence interval, which is the standard thing to do. Let's move on to the non-athletes. The non-athletes have a different X-bar, a different standard deviation, and also a different sample size. But we'll use the same formula. The formula is, again, sigma over the square root of n. We have the standard deviation from the sample, so we'll plug that in here. And we get 1.5 over the square root of 400, which is 0.075. So then that's the value that has to be doubled in order to produce the margin of error. And so we'll make the confidence interval by starting with the measure 3.0 now, plus or minus double 0.075. And that will give us a range of values which extends from 2.85 to 3.15. And again, the meaning of that confidence interval is that somewhere in this range, the true average GPA of the non-athletes at the whole school should reside. We can say that with a confidence level of 95%. Now, here, the striking thing about these numbers, if we're thinking about policies of the school or academic support, is that the athletes have a higher GPA than the non-athletes. We could explore why that might be true, but they're made up numbers, so we don't need to go into details. But the question we might ask ourselves is that really true at this school? It's true of our sample, and it's true of this sample, I mean, if comparing our samples, but is it really true at the school? Well, all we're concluding with confidence here is that the average GPA of the athletes is somewhere in this range, and the average GPA of the non-athletes is somewhere in this range. As you can see, there's a very broad overlap between these ranges. And so the accuracy of our measurements is probably not even sufficient to clarify whether the athletes indeed have higher GPA than non-athletes. But in order to really sort this thing out, what we need is a confidence interval for the difference, because we need to be reasoning about the difference between the average GPA of the athletes minus the average GPA of the non-athletes. So we need to reason about the difference between these two averages. And so we have a measurement of that difference, but we need to also reason about the possibility of error in that measurement. So the measurement for that is 3.1 minus 3.0, which is 0.1, right? The measured value of the GPA of the athletes minus the measured value of the GPA of the non-athletes gives us a measurement for the average across the entire school. But now we are faced with a familiar problem. We have a measured value of the difference, and we want to produce a confidence interval for the difference, but we need a standard error in order to produce a confidence interval. We have a standard error for this one. We have a standard error for that one. We need a standard error for the difference between them. And this is where we're going to use this combining formula for the standard error. The standard error for the difference is again going to be the square root of the sum of the squares. Standard error for the athletes, standard error for the non-athletes. We're going to square them both, add them, and take the square root. So this will be the square root of specifically 0.08 quantity squared, and over there 0.075 quantity squared. And this will work out to be approximately 0.11. So that's approximately 0.11. And that is a standard error not for the athletes' GPAs, not for the non-athletes' GPAs, but a standard error for the difference between their GPAs. Now, if we want to make a confidence interval for the difference between the two GPAs, then we take the measured value, which is 0.1, and we plus or minus double this, this standard error, 0.11. So that'll be double, will be 0.22, of course. And so that'll give us the range from negative 0.12 to positive, should be 0.32. So adding and subtracting 0.22 to this 0.1 will give us the range from minus 0.12 to positive 0.32. So what on earth does it mean? Understanding what that means is the key thing here. This is not the confidence interval for the athletes. It's not the confidence interval for the non-athletes. It's the confidence interval for our prediction of the difference between them. What we're really saying here is out there in the school generally, the athletes have a certain GPA, the non-athletes have a certain GPA, and there is some, out there in the school generally, some difference between the true GPAs of the athletes and the non-athletes. And this is our prediction for where that will lie. The true answer here is somewhere in the range, for the true answer for the difference between them is somewhere in the range minus 0.12 and positive 0.32. So what we're saying here is it could be as extreme as the athletes are better in terms of GPA by 0.32, right? If the difference was positive 0.32, that would mean the athletes were doing better. So the difference could be as much as the athletes outperforming the others by 0.32 on average. Or it could be the opposite, that if the difference is negative, the athletes are worse off. It could be that the athletes are doing worse by as much as 0.12. Or it could be, because 0 is in between here, it could be that there's no difference at all observable at the school. And so this confidence interval for the difference explains to us what is the correct deduction to make about the difference. It's tempting to just look at this 3.1 and look at this 3.0 and say, oh, the athletes are doing better. If we produce a confidence interval for the difference, we get the truth of the matter, exactly what we know and how confident we are about the true difference between athletes and non-athletes. And in this example, there's no confidence statement that we can make about who's doing better or who's doing worse, because the confidence interval extends from the negatives to the positive. It includes negative values and it includes positive values for the difference. And so both possibilities are real possibilities even after we collect all of this data. So as is the usual case here, if you want your confidence intervals to get narrower, then you need to measure things more precisely. And if you want to measure things more precisely in statistics, then you need larger sample sizes. If we, for example, quadruple the sample size here, quadruple the sample size here, then the standard errors will go down by a factor of 2, and then all of these confidence intervals will shrink by a factor of 2. And if we continue increasing the sample size, we can get these confidence intervals to get narrower and narrower and narrower. We can hope to get a very precise measurement, and then we'll measure the truth of the matter, which population is doing better or worse than the other. But with these sample sizes, we can't measure that level of accuracy, and so we get an ambiguous answer. So that's how we use the standard error for the difference, using the combined formula for the standard error of the difference to produce a confidence error for the difference, and that's how we interpret it.